Hey guys, welcome to the fifth video of Module 7. And here we are going to talk about the commonly used activation functions in our deep learning models. Starting with sigmoid, then we'll be talking about the hyperbolic 10, that is the 10h activation function, then the ReLU, and lastly about the softmax. So let's get started. Now before we jump and look into some different type of activation functions, let us first of all understand that what do we mean by the activation function itself, and then why do we even require it for this kind of neural networks. So this activation or the transfer function, whatever you like to call it, it is used to bring this sort of an non-linearity in the neural networks. And this non-linearity helps the network itself to learn the complex underlying patterns that we have in the data. If you remember, I talked about that hidden layers are very much responsible to decode this kind of underlying features that we have that are going to be responsible in between input and output layer. Basically, all the kind of complex patterns and relationships that we have between the input and output are decoded with the help of this kind of hidden layers. So how is this possible? It is possible because of this kind of activation functions. This activation functions, if I talk about in when they're connected with this bunch of different neurons, it sorts of brings in this kind of non-linearity, and because of which we are able to decode this kind of complex underlying patterns. And without this, we know that neural network is simply going to depict like a linear regression. For example, if I talk about only, let's say, this particular neuron, if I don't activate this particular neuron, it's simply going to be unactivated output, which is something like x1 into w1 plus x into w2, so on and so forth, plus the bias term. And then on top of that, let's see, if I include sigmoid activation, then this particular neuron itself connected with this input neurons are going to work like a logistic regression. But then if I combine this particular neuron with bunch of neurons in this hidden layer, if I have multiple hidden layers, this kind of things all together brings in the non-linearity that we are talking about over here in some way, so that it is able to decode this complex underlying pattern in the data, such that we are able to decode this kind of relationships between the input and the output layer. So that's the main purpose of having the activation functions in your architectures. And yeah, that's about the activation functions. Now let's look into some of the different type of activation functions. And the first one that we are going to look into over here is the sigmoid activation function. Well, we have already covered this in one of our previous modules. I'm not really going to focus a lot more on this, but still, to give you a quick summary, this is how the activation function of sigmoid looks like mathematically, and graphically that's how it's going to look like. We can clearly see it's a squeezed graph where the values are in between 0 to 1 as a part of the output. Inputs could be literally any values from the negative infinity to the positive infinity. And over here, the base threshold that we have is set to 0.5. Well, manually, you can try to tune this kind of threshold depending on the type of problem that you're solving. But commonly, we have it on 0.5. So any value that will be greater than 0.5 will correspond to that particular neuron to be activated. And if it's less than 0.5, that particular neuron will not be activated. When I say it's activated, it means the neuron has fired. It means that it is now going to be connected with the further neurons. And if it did not get activated or it did not get fired, it means the connections are going to be broken. That is, like if that particular neuron is connected, and let's say, for example, I'm talking about this neuron. If this neuron is not activated, all of these neurons, the connections that it has with all the neurons because of these neurons are going to be broken. So yeah, that's something you need to keep in mind when I talk about activated or it won't be activated. So yeah, similarly, if I talk about the 10h activation function, it is also known as the hyperbolic tangent function. And in mathematical function, this is how it's going to look like. And graphically, that's how it's going to look like. This time, the output values are squeezed in between -1 to +1. And again, it can take all the inputs from the negative infinity all the way up to the positive infinity. Now over here, the threshold is set to the value of 0, not 0.5. So for a particular neuron, let's say that the output of the 10h activation is going to be less than 0 and 0 is the threshold. Then that particular neuron will be not activated and therefore not fired. And because of which, all the further connections will be broken. And if, let's say, the output of that neuron was greater than 0, in that case, that neuron will be fired and all the respective connections with that neuron will be activated. And just like that, we are having one more activation function. This time it's not a squeezed function like sigmoid or 10h. This is having a value that is always going to stick to 0 if the inputs to this activation is going to be negative or even 0. And right after that, any positive value that it's going to take, the output will be equal to that positive value. And this type of activation function is called as rectified unit, or we can also call it as ReLU activation function. So as you can see, ReLU outputs a value from 0 to infinity. And then f of x returns 0 when the value of x, that is the input, is less than 0, as you can see from this graph. And then f of x returns the value of x, the same value as the input actually, when the value of the x is positive. For example, if I pass the 5 as the unactivated output to the ReLU activation, the output is in itself going to be 5. It's not going to change itself. But yes, if the input to this ReLU was, let's say, negative 2.5, it will change the value to 0. Then neuron won't be activated if the value of x is less than 0, or if the output of the ReLU is 0. In that case, neuron won't be activated or won't be fired, and therefore all the respective connections will be broken further. And then if the neuron is activated, that's the condition when the x stays positive, or when the output of the ReLU activation is equal to the input that it had got. In that case, the neuron will be activated and the respective all the connections will be also activated. It is usually implemented in the hidden layers that we see in the neural networks. Apart from this, there is one more activation function that I'm going to talk about, which is the softmax activation function. And this is something that we have also discussed in the previous video. While we were talking about that, how do we decide the number of neurons that we'll be having in the output layer? So yes, if you remember it, we use softmax activation for the multi-class classification. So on the final layer itself, we know that that's where we are going to have the final output, whether it's going to belong to class 1, class 2, class 3, or as many classes that we are having in that particular network. So the way it works is, it gives you the probability for each and every class for it to be the output. For example, over here, I have considered 5 different classes. So what is the probability for it to be classified as class 1? It's 2% probable. What is the probability that it belongs to class 2? It's 90% probable. Just like that, we are having multiple different outputs, and all of these values are such that if you add them together, it's going to be equal to 1. We are normalizing this kind of things, and therefore it's going to be equal to 1. So the way it works mathematically is, these are the outputs that we get from the unactivated outputs, basically for the output layer, or the output neurons in the output layer. So let's say, for example, the first neuron had the unactivated output as 1.3. How do we activate it? We do e to the power of 1.3 divided by the sum of each and every of this e to the power of 1.3 plus e to the power of 5.1 plus e to the power of 2.2 all the way up to e to the power of 1.1. So the denominator will always be the same for any kind of probability that you calculate for respective classes. But the top part will keep on changing. So if I'm talking about class 1, what is the probability of class 1? So e to the power of 1.3 divided by the summation of all the e to the power of 1.3 all the way up to e to the power of 1.1, the output is 0.02. You can calculate this with the help of your calculator, and correct to 2 decimal places, you will see that the answer is 0.02. Similarly, if you want to calculate the probability of the class 2, it's going to become e to the power of 5.1 divided by e to the power of 1.3 all the way up to again e to the power of 1.1. And then if you do this calculation, the output is going to become 90%. Just like this, if you calculate for class 3, class 4, and class 5, these are the respective probabilities. And then if you add it together, it's going to be approximately equal to 1. And now over here, the probability which is the highest is the class that it belongs to as the final output. So the final classification of this particular thing is class 2. So this is how basically a softmax activation function works. So by the end of this video, I hope you were able to understand the whole point of having activation functions in deep learning. That is what is making it really very special. Now in the upcoming video, I'll be starting by creating the deep learning model from scratch, and it's going to be really very amazing. So stay tuned for that.